Hi, I'm Jim Bergman, Chief Technical Officer, TruTech Tools. Today's presentation is called Introduction to the Testo 550. We're going to go over a transition to digital technology. Old school tools of the trade consisted of gauges for each refrigerant. If you remember, if you've got any time in this industry, we used to have gauges for for R12, for R22, for R502. We had separate sets for each. We had temperature pressure charts, we had thermometers, we might have carried a calculator just to calculate superheat and subcooling, a pen and a paper to record our readings, and today a lot of things have changed. Although, when you look at the old school technology, we've been using the same technology for the last century and a half. Albeit today it's more precisely manufactured and with a lot of care it can produce readings that are okay. Most of these gauges were in specifications when they left the factory, but only to 323%. And the question becomes, is close enough good enough? A standard 323 gauge means that, from the first third of the gauge, it's plus or minus 3%. The second third of the gauge, plus or minus 2%, and the last third of the gauge, plus or minus 3%. So what this means is a standard gauge, from 0 to 40 is plus or minus 3.6 psi. From 40 to 80 is plus or minus 0.2.4 psi. And then from 80 to 120, again, plus or minus 0.3.6 psi. Now, when we take a look at a high side gauge, that becomes plus or minus 10 in the center of the span, and outside the center of the span is plus or minus 15 pounds. Now, what you got to realize is, we're talking on the low side gauge, anywhere within about a 5-pound span is considered accurate, and on a high side gauge, anywhere within a 20-pound span is considered accurate on that gauge. When we look at a 1% accuracy gauge, a little simple math, 1% of 350 pounds is 3.5 psi, which means we actually lost ground. If you remember in the last slide, it was 2.4, now we're at 3.5 psi. On a high side gauge, we did gain a little ground because now 1% of 800 is 8 psi, plus or minus 8. But still, we're looking at plus or minus, or 3.5, which is a 7-pound span, or 16-pound span on a high side. Now, if you stop and think for just a second on a temperature pressure chart, and this is where some of the problems lie, is, if we just look at over here, if you follow my mouse cursor over here to 90 to 95 condensing temperature, we're looking at a pressure 168 to 181. And, where in that span do we fall? It leaves the technician to interpolate the gauge. You got the inaccuracy of the gauge, and now we got to take that pressure that we've interpolated, that's plus or minus at 16 pounds, and apply it to a temperature pressure chart, and then turn around and calculate superheat and subcooling of that value. And odds are you're not going to be able to do a very good job of getting even within a few degrees of the correct subcooling. Before we go too much further, it's important to understand too that not all digitals are new technology. Some of the digitals coming out today that you'll see are simply an analog gauge with a digital display. And this gives us all the inherent problems of analog with a digital display. So, in this one here, we're looking at the back side of the gauge opened up. We got a strain gauge connected right to a bourdon tube. And, so you've really got to, when we talk about digitals, we're not just talking about a digital display. We're talking about a purely digital gauge. This kind of stuff is like deja vu all over again. So are there really problems with analog instruments and the procedures and measurements? Well, let's just look at some facts. The California Public Utilities Commission did an analysis of 13,000 residential and commercial units. Most were off by about 1/2 to 5 pounds of refrigerant. AC units off by more than 8 ounces, they found would potentially fail within 5 years. And cap tubes or short orifice systems, even an ounce or two, could have a serious impact on performance. But at the end of the day, what they found out is 74% of units were incorrectly charged. Causes were improperly calibrated measuring equipment, human errors during commissioning, and again, this is sourced from the California Refrigerant and Airflow Verification Program. Similar study done in North Carolina on new heating and cooling units. 90% of all the units tested exhibited some sort of energy waste problem. 50% of all the installations had improper refrigerant charge. 40% failed to meet minimum requirements for airflow standards, and a 20% reduction in airflow will reduce the SEER about 17%. 15% return air leak from an attic with a 120 degree attic will easily reduce a SEER 12 down to SEER 6, so about a 50% loss. But just looking at charge on this thing, 50% of all units had improper charge in the study. Arizona Public Service Company. Again, skimming down through this, improvements to duct leakage, 16% savings. Improperly insulated ducts, 42% loss. 64% of units tested had airflow less than 350 CFM per ton, with an ideal being 400. 82% improperly charged. Average improper charge reduced the efficiency by 31%. Technicians frequently weren't using micron gauges, and 53% of the units were oversized, causing wear and tear and thus higher energy costs. But these are just staggering numbers. Energy Star did a study in 2006 on proper charge. They found essential charge is essential to maintain capacity. Improper charge led to premature compressor failure. Up to 41% of systems were undercharged, 33% were overcharged, an average savings of 12.5% with proper charge. The charge was adjusted by the technicians, and here's the key one: systems with more than a 3-degree deviation in subcooling from the manual spec would not qualify for the Energy Star label. When they were doing the study, that's what one of the things they were trying to determine. So the charge had to be within 3 degrees of subcooling of the manufacturer spec, or would not qualify. Now, just think back for a second here. If we're plus or minus 16 pounds on a 1% accuracy gauge, and then we also have the temperature pressure chart we got to interpolate. We also have maybe possible measurement in our temperature measurements. So trying to hit these numbers would prove to be next to impossible with analog tools. The key thing when you add all this up here is 41% of systems were undercharged, 33% overcharged. Again, 74% of systems had improper charge in this study. So what has all this led to? High rates of system failure, unnecessary warranty claims, poor system performance, loss of confidence for both the consumer and technicians, high utility bills, callbacks, dissatisfied customers. It's really a chain of events that's led to a mess. When you stop and think sometimes that, and I'm sure you guys have all seen it, the old refrigerator plugging along in somebody's garage. It was it's charged in 1950, and the thing's still keeping beer cold in somebody's refrigerator. And if it got dirty, if it quit working, we'd see if it got dirty. We'd clean the condenser. We might clean the evaporator. We might vacuum underneath the refrigerator. But the last thing you do is open it up and check the refrigerant charge. And that's really what we should be doing today. I mean, it's it all comes down to that old refrigerator was properly commissioned and properly charged. And now all it needs is just maintained, and that's the same thing we got to do today. Yet it seems like it's the last thing we do, and the first thing we do is we hook gauges up every time we go on a system. And so these types of things, if we start these things up properly, get them running properly to start with, well, then we're going to eliminate a lot of our problems with operation on the back end. My question is, techs, 74% of systems have an incorrect charge. Are you finding them that way, or leaving them that way? Really what it comes down to is today is tools and procedures, and the answer is good instrumentation. A lot of technicians don't have it. They have substandard instrumentation. It's out of calibration. There's a lack of training. They're using incorrect measurement techniques. They're using the wrong tools for the job, and everybody's doing their own thing. Today, what we'd like to recommend you guys look at is a Testo 550 Kit 2. It consists of 2 temperature probes, a meter, and a case. What's not required are any calculations, any other temperature pressure charts, any interpolation, extra thermometers, or separate gauges. This is really an all-in-one tool. The Testo 550 is really engineered to be a perfect balance between features, benefits, and cost. It's really for what you pay for a product like this. It's in the sub $300 level in a lot of cases. It's really a great value. It's designed specifically for charging, troubleshooting, tightness testing, evacuation, and recovery, and we're going to cover all those in some detail. Some features of the 550 are really probably number one is low initial cost. Testo really went back to the drawing board to make a digital gauge set that would be affordable for the average technician. And they also wanted to do a low continued cost of ownership. If you have any history with digital gauges, you might remember, probes were very expensive to replace. Some of them were not field grade instruments, where they wouldn't take a lot of abuse. And so now, Tesla's addressed a lot of those concerns and made those things a thing of the past. They're all user configurable units of measure. They do simultaneous measurement of superheat and subcooling. They have altitude compensation adjustment. Really cool feature. Allows you to adjust the instrument for very precise measurement based upon your altitude and your barometric pressure. They do standing pressure tests with temperature compensation. We'll cover that a little bit further. They have a min-max-mean function, delta temperature calculation for like checking temperature drop across dryers, and they even have field replaceable valve assemblies. The digital manifold, the Testo 550, comes with 33 refrigerant profiles included in the instrument. New ones like R410A and R404A, and some of the older ones like R12, R22, R507. The refrigerants on this particular unit cannot be updated via the customer. The only place it can be updated is through Testo. If you look at the specifications on this thing, it's rated for use with CFCs, HCFCs, HFCs, nitrogen, and even water if you want to use it for like water balancing. There's 33 profile refrigerants built in. It's got 3 1/4-inch SAE ports, and then uses 2 pluggable NTC thermistors for temperature reading. The measurement range on both sensors is 0 to 580 psi. They're actually matched pressure transducers, but it's got a working pressure range of up to 870, and overpressurization is actually closer to 1080. The temperature measurement range is -58 to 302. Accuracy is 0.75% full scale, and temperature plus or minus 1.8 degrees. Usually you're looking at resolution of about 0.1 psi, and temperature about 0.1 degrees Fahrenheit. Very fast reaction time on the display, a half a second, and the batteries last about 40 hours without the illumination. Construction features. Now what makes these different? We talked about board-on tubes. Well, board-on tubes are no longer in any digital gauge, a true digital gauge. And Testo uses a thick film pressure transducer, which is actually a ceramic pressure transducer that is very, very rugged, and will hold its calibration for an extremely long time. The low mass temperature sensors that are included with the instrument allow it to get very quick, precise measurement. It's got a standard 3-way configuration through the valve block, so it's just like a standard set of gauges you would use. A magnifying sight glass, you can actually see if there's particulates floating around if you let a little liquid from high to the low side. Integrated hose parks and a hook. A metal manifold construction. It's an aluminum valve body, brass connectors on the bottom, and very, very simple to operate. Couple things about the low mass temperature sensors. I have one sort of cut away here, the brass barrel. I cut it off so you could actually see what's inside of it. And it's an NTC thermistor, which has a measurement range of -58 to 302. And thermistors have a huge advantage over K-type thermocouples in the fact that they have very large temperature sensitivity. They have good electrical noise immunity, which is critical when you're talking about a digital gauge set, because anytime you run refrigerant through a hose, you generate static electricity, and K-type thermocouples are very susceptible to temperature error when they're exposed to stray electrical current. NTCs versus platinum thermistors now made a much lower replacement cost of the probes, and the probes are all electrically shielded. I also, these are clamp style probes, and a lot of people always, wondered, well, does that clamp affect the temperature reading because it's exposed to atmosphere? And I took a thermal image here, and you can actually see, the blue here, the suction line, and then the blue of the brass barrel connected. It does a very good job at reading temperature on that clamp probe that's reflective of what the suction line is. You can insulate it if you want to, some additional assurance if you got a lot of wind or stuff blowing around there. But the temperature probes is designed to do a very good job at getting a measurement that's reflective of what you're seeing on the line. Digital technology, we talk about that, it's really what we consider a digital window into ACR systems, because the superior accuracy, the greater speed, real-time calculations, and it's an all-in-one tool. The other thing with digital gauges that you can't do with analogs is confidently charge at low ambient temps, and I'll show you a slide coming up here on how that's done. But it really leads to fewer callbacks, increased profit, and increased profitability. The gauges today are really laboratory accurate instruments designed for rugged use in the field. A couple features I want to highlight of the Testo 550. It precisely measures the pressure using the ceramic pressure transducers, and then automatically calculates or displays the evaporating and condensing temperatures for the selected refrigerant. So when you enter the profile in, you tell it's R22, and it reads a pressure of 68.6. That's displaying a temperature of 40 degrees. That's the temperature of the evaporator coil. And then it also displays the temperature of the condensing coil right on the display. So there is no temperature pressure chart that you have to carry. It's going to display those automatically for you. Simultaneous superheat and subcooling. There's two externally connected temperature probes. You connect one to the liquid line, one to the suction line, and you get very accurate results with those surface probes. They very quickly respond to changes in temperature, and then automatically, using that refrigerant profile, calculate the degrees of superheat and subcooling. Evacuation recovery. A lot of guys wonder, can I evacuate and recover through a gauge set like this? And yeah, you can, absolutely. The vacuum on these, though, is what we call a gross vacuum indicator that reads inches of mercury. It's not a micron gauge, so we're talking about something that you're going to use to look at the roughing of your vacuum pump, or to determine if your level of vacuum is adequate for recovery when you're recovering refrigerant. If you want an exact vacuum measurement, you really need to use an external vacuum gauge. Tightness test. Now, this is one of the neatest features of the instrument, and it's one of the things I think is probably one of the more underutilized features by a lot of technicians, just because they haven't delved this deep into the product. But the tightness test allows you to basically record an initial pressure and temperature, and start a standing pressure test. And when you start that test, it records the initial pressure on the left-hand side of the gauge, it shows the final pressure on the right, and then it shows the difference in pressure between the time you started the test and the time the test is stopped. Now, the cool thing is that Testo uses a temperature compensated pressure test, which basically works off the gas laws. It says, when you have a fixed volume and a gas inside that fixed volume, if the temperature of that gas changes, so does the pressure. And so what this allows you to do is clamp a probe on the suction line or on the liquid line, just somewhere on the system, so you can get the temperature, and charge that system up with an inert gas like nitrogen, and then start the pressure test. And then 20 minutes later, you can come back and see or has the pressure changed or not, and B, is that system leaking or not, because the temperature compensated tightness test will allow you to determine whether that pressure could have changed due to a temperature change, or whether that pressure change was actually due to a leak. So that's a very powerful feature. The reason you want to use a temperature compensated tightness test is, number one, it assures the system's tight after assembly and prior to evacuation. It uses the gas laws to account for changes in temperature during the test. It quickly reveals if there's any leakage present. And you've got to realize, too, you're reading at tenths of a PSI. It records elapsed time for pressure testing, and it also will finding a leak under pressure avoids drawing moisture through the system when you're doing an evacuation. So this is critical with 410A systems. We want to keep these systems clean, dry, and tight. So what we don't want to do is put a system on a vacuum pump and find out that we have a leak, and we've been sucking atmosphere in for 30-40 minutes while we're trying to get our micron gauge to read, only to find out that we have an improperly brazed joint or something like that. The digital does it better for a lot of reasons, because number one, it allows some trending and allows us to complete more complex functions. The higher accuracy is going to reduce callbacks. It's going to do calculations without human error. It's going to stay in calibration much longer than analog gauges ever will. It's got very high repeatability, excellent reliability, and plus digital gauges are really cool. They're really a nice way to separate yourself from your competition. We talk about refrigerant charging. We're really talking about plus or minus 3 degrees, but on subcooling, and that just brings us to the point that it's critical for proper operation. With a 550, we can charge directly by superheat and subcooling, and an interesting thing is you can see what's happening in real time instead of what's happened. And you got to remember, when you're doing an analog calculation of superheat, you're measuring a pressure, converting it to temperature, finding the liquid temperature or the suction temperature, and subtracting it from the saturation temp to get a superheat or subcooling reading. Well, by the time you're done with that whole process, who knows what's changed in the system? If there's any kind of hunting or any kind of changing, the load's changing in there, you really aren't seeing what's happening in real time. And again, the Testo 550 works with 33 of the most common refrigerants. With the dual temperature inputs, we get a direct display of superheat and subcooling. So as you can see on the display right there, looking at 9.7 degrees of superheat, 13.3 degrees of subcooling at a pressure of 52 pounds and 181 psi on the high side. This allows the technician, when you got to charge the system by subcooling, to actually see the charge directly by subcooling and then see what's happening on the low side of the system, make sure that valve is actually doing what it's supposed to do. This really aids in troubleshooting and in getting it right the first time. Interesting thing is, when you look at a system, especially if you charge the analog gauges, and you've seen a system like this one here graphed below. This was done on a Testo 556 with recording capability, but the idea behind this falls true with all Testo digital gauges. You can see, if you look at my cursor on the top here, this red line on the top is the high pressure side, and that high pressure was fluctuating up and down. And on the low side, the pressure is fluctuating up and down, and then the green line down here is the corresponding saturation temp, and the light blue line is the measured temperature. So the difference between the saturation temperature and the measured temp is what we're saying is superheat. And you can see how those lines, the peaks and valleys, almost mirror each other between the measured temperature and the saturation temperature. And what that results in is a superheat line across the bottom here that's almost flat. Now with a digital gauge, the digital gauge sees that 7 to 9 degrees of superheat. That's what it's reading, because it's measuring temperatures and pressures at the same time. And with the low mass temperature sensors and the fast response to those pressure transducers, it's actually seeing a constant superheat and allowing us to charge and work on this system, which, if you look at that saturation temperature, is operating somewhere around 34-35 degree coil, which means we're just above freezing on that evaporator coil, and at the low end where the valve is actually starting to hunt due to a low load. But what the digital gauge is allowing us to do is charge at this low ambient without having any problems with actual without having any problems of having to interpolate what the actual superheat and the subcooling actually is. So we get a lot of common questions and answers. I want to review those now. Grounding. Everybody, this has been a big deal. If you've been on any of the forums and stuff, everybody goes, "Oh, I never had to do that with analog," and it's interesting. People are saying that, but this has been a problem. This is a problem with all gauges. I don't care whether they're analog or digital. It's just the thing with the digital gauge is you got electronics in there that are susceptible to damage, and if the gauge isn't set up or engineered properly, you could have problems. So it's just something you got to be aware of. Refrigerant's a dielectric, and when it passes through a rubber hose or a hose, static electricity is generated, just like a Van de Graaff generator. And these static charges can be as high as 15 to 20,000 volts. It's just like walking across a carpet and you shoot a spark off your finger. Okay, exactly the same thing. There's a grounding strap, and now this grounding strap is not required on the newer 550s, but on the older 550s it came with a grounding strap. You clamped one end of the 550, you clamped the other end to the equipment. The newer 550s, this is done through the probe, and I'll cover that in the next slide here, I think. But you use that grounding strap when you're adding or removing refrigerant to a system. On a newer 550s, If you're adding or removing refrigerants, just have a probe plugged in and have it clamped to the system, and it'll eliminate any kind of static discharge to the gauge set. That grounding strap should be the first thing on and the last thing off the system. And again, I told you grounding is done through the temperature probes on the newer 550s, eliminating that step. But the temperature probes, if you look at a newer 550, an easy way to tell is if your gauge came with a temperature probes with green O-rings on there, then those are grounded probes. Now the key thing is here is you can't say, oh, well, just buy new probes and I won't have to mess with that grounding strap anymore, because the newer 550s also have some changes on the board that allow these probes to work with that. The older 550s, you always need to use that grounding strap on. So it's just what I did is I wire tied that grounding strap to my hose, and when I connected my suction to the my hose to the suction line, I clamped the clamp right there with it. So it's just something you just got to be aware of, and it just protects the gauges from damage from static. Cross-contamination. What do I need to do when switching types of refrigerants? At minimum, you need to vent that residual refrigerant from your hoses, install and purge the hoses with the refrigerant you're working with in the system. While not required, we recommend that you consider using 2 sets of hoses, one for POE and mineral. And then, when those hoses are disconnected from the system, obviously you want to use a quarter by quarter flare connector to keep those hoses tight so that oil doesn't absorb any moisture. Or if even a better option is to consider a second set of gauges to avoid cross contamination of systems, especially if you're a residential tech and you're doing R410A and 22. It just makes it easier, and if you're, with many of those types of systems you run across, having a separate set of gauges is nice. And then you also got a spare set when you get on systems with dual compressors or something like that. So that would be my personal preference, but again, it's a recommendation, not a requirement. Pressure ratings for 410A. This was an interesting question we got. The gauge manufacturers say you have to be rated for 800 pounds pressure for 410A, yet the 550 is only rated at 580 pounds working pressure. And a lot of questions, is the 550 safe for 410A? And the answer, oops, let me back up here. The answer is absolutely. Okay, the gauge manifold set, you got to remember, gauges are rated off the center of their span. So those highlighted areas right here on the oval right here is the most accurate span on that gauge. So you're talking from 100 to 200 pounds is where that gauge, where they want it to be very accurate. That's the typical working pressure for 410A on the low side. The high side, we're looking at somewhere between 275 and 450. So again, you're talking the center of the range in the gauge. In order for that gauge to be highly accurate in the center of its span, it's got to have on the high side 0 to 800, and on the low side 0 to 350 pounds. So all gauges, again, have to, in order to be accurate, they have to be designed to operate in the center of their span. When we're talking of pressure transducers, the transducer is selected for the most accurate measurement range desired. And a transducer, unlike a gauge, can handle large overrange without damage. So, even though the transducer has a working range of 0 to 580 pounds, its accuracy is going to be much, much higher because it's a lower range. So now instead of 0 to 800 like a gauge, we're looking at 0 to 580, and then we're looking at 0.75% of full scale. So we're looking at a much higher accuracy overall because we've got a transducer that's selected that meets the measurement requirement, but will handle the pressure requirements even in an overrange. And just stop and think for a minute, because on a typical 95-degree day, we got condensing temperatures that are 110 to 125 degrees, resulting in pressures from 364 to about 439, which I got sort of in that green oval on the box there. And up to about 116 degree day outside on a 10 SEER piece of equipment with 410A in it, the 550 would work fine. So unless you're constantly seeing days over 116, really not a lot to worry about. Okay. The 550 can stand an overpressurization of 1080 psig, so it's perfectly safe for 410A. Vacuum. A lot of guys want to know, can I measure vacuum with a 550? You can measure gross vacuum with it. In other words, it's not a micron gauge. It can be used during the evacuation process, and it'll indicate your pump is pulling down till the point where your micron gauge starts to read, but it doesn't have the resolution of a micron gauge, and we still recommend using a micron gauge during evacuation. If you're going to evacuate properly, you really don't even want to have gauges hooked to the system. We recommend that you look at the Appion MegaFlow kit, which includes oversized hoses, a vacuum-rated manifold, vacuum-rated core tools. If you're doing large systems, a TES 8 vacuum pump for the evacuation. But the MegaFlow kit can be used on residential or commercial. And then, vacuum gauges, thermal analog micron gauge is a really good thermistor gauge if you want an analog set. If you like digital, the digital BlueVac by AccuTool is an absolutely awesome product. Reads tenths of a microns, temperature compensated. Excellent for refrigeration because it also works for low temperature applications. So that's another product you may want to take a close look at. What's the warranty? Warranty on the 550 is 2 years, probes and meter, due to defects in material or manufacturing. So, Tesla really designed this thing to withstand some field abuse, and it is rugged. Tesla does a great job supporting the tool, so those types of things you really don't have to be concerned with. So thanks a lot for your time and attention, and if you want to know more about the Testo 550 RSA, visit us at www.truetechtools.com. And again, I'm Jim Bergman. Thanks for your time and have a great day.